Okay. So remember that we started with the diffusion equation the last time. Delta rho by delta t is d times del squared of rho. We said that d was a diffusion constant. The dimensions of d was a length scale L squared divided by the dimension of time. So it could be something like meter squared per second or centimeter squared per second, depending upon what is more appropriate to describe the system that you're thinking of. Okay? Rho here is rho as a function of space and time, which we interpreted as a density of particles. If you integrated rho over the entire volume, so suppose rho of x comma t dx, you got the total number of particles in that volume. Okay. So then we wrote this in some different ways. We said, let us introduce a quantity j, which is minus d times the gradient of rho. So this is the gradient of rho yields a vector. This is a scalar, but applying the gradient operator yields a vector. This is another vector on the left hand side. And this is a current, a particle current. And with this definition of j, we have delta rho by delta t is minus del dot j. And there is a special significance to writing this equation in this particular form. This, as I said, is called a continuity equation. And this reflects the fact that particle number is locally conserved. That's what this relationship actually says. The current J, this is the calculation of the current in one particular case where I have a bunch of diffusing particles with diffusion constant D. But in general, J is, suppose I have particles moving with the local velocity c at position x at time t. If I multiply this by the density point x and t, this is a quantity that is also a current, but is a current associated with some systematic velocity of the particles at point x at time t. For example, suppose every particle here, suppose there were a bunch of particles at density rho naught, assume that to be a constant, and they were all moving in this direction with, say, some v naught times x hat. So this is this vector c here. Okay? In that case, j would be directed along the vector x hat and would have magnitude v naught times rho naught. That's how we would write the current in that particular way. Okay? The interpretation of the current is the number of particles per unit time. Well, actually, instead of current, I should say current density, strictly speaking, per unit time crossing an infinitesimal area ds, crossing an infinitesimal area ds normal to that area.
So the number of particles are conserved globally?
The number of particles are conserved globally, which is this statement, but it's also conserved locally, which is what we were trying to say. We said that if the particles are conserved here, I have some bunch of particles here. The only way this will change in time is for particles to leave the surface, either to come in or to go out. So then we said that the total number of particles leaving the surface per unit time would be given by an integral over the surface ds dot j. By dotting it with the surface, this now becomes a number per unit time. So this is the number of is the number per unit time of the change across this particular surface. Okay. Let's just see if there's any way we can justify this j dot n term here. So by saying ds, what I mean is I have a surface here. I break that surface into little bits of area, Each of these might have some magnitude ds. It also has a vector, unit vector attached to it called n hat. So then this vector ds which I wrote here is just the magnitude ds times the direction unit vector n hat. Okay? So why is this particular form useful? Here's one way of thinking about it, that is to suppose I have some, let me say, a pipe in which water is flowing out. So the pipe might look a little like this. Suppose all the water is actually going in this direction. So the number, if you can ask, what is the number per unit time that is crossing the surface? Well, everything that is within a region v times delta t of this exit point, in time delta t will have moved outside. Okay? And if I v times delta t is into, so this would be a length, into this dimension here, let me call this h, is the total number, so this is a length times this is an area, times a density here is a number that are crossing per unit time across that. Okay?
What is C actually?
C is a velocity. So in general, I can always write a current as a velocity times the density. And this is the velocity with which particles are moving over there. Okay? So this is the total number that are moving across here per unit time, across this little surface here, ds. And ds might be, if this is a square, this is h squared here. So let's just see that our dimensions are correct. This is, so what I want to do is number of particles leaving per unit time. I said all the particles per unit time, let us say, so in time delta t. So I said all the particles that are contained within the region v times delta t are the particles that will move out. To find the total number, I have to find what is the volume. So v times delta t times h squared is the volume of this little square. All of the particles inside this volume will now move out. Multiply by delta t, that is the time that it takes for all of them to go out. Okay? So now this is a number because this is a density. So this is the number per unit time because there's a delta t here. Okay? Because this is in time delta t is proportional to delta t, and all other quantities are adjusted so as to give you the right answer. Okay? So now this h squared here is the analog over ds. And because the velocity vector is in this direction and the normal to the surface is also in this direction, we needn't worry about the dot product. But now we can imagine a different situation where we take essentially the same system, and I just imagine cutting it like this. So if I looked at a cross section of this, this might look like, okay, say like this. All I've done is cut it. That doesn't change the amount of water flowing because it's just cutting the pipe at some point. The amount of water flowing is determined by the rate at which I input it at some very far end on the left. So by cutting the pipe, I have not changed anything. What I have changed, however, is the way I describe the system, because now the surface area that I have is now this surface area, and its normal is now pointing in this direction.
So the edge was the height.
So, yeah, so in this earlier case, this was h and this was h. It was just a square cross section.
So this gets changed here.
So we'll have to see exactly how it's changed and sort of account for that when we do. So now over here, the velocity with which it moves is still in this direction, but it's just that the way I define this normal to the surface has now changed. So let us now see how that changes, what happens to that j dot n hat here. And this should also be multiplied by a ds. So as you said, suppose I have now cut it at an angle which is, let us say, how do I best define this angle? let this angle be something like, call this theta. So then ds becomes ds divided by cos theta. It should not be theta. I think theta should be probably this angle here. Okay. So now when theta is 0, the angle cos theta is 1 and ds is your usual answer. J and then point in the same direction.
How is ds? It's normal.
So now ds is this little surface here. I want to say what is the difference between ds here and ds here. Now the point I want to make is, having cut it like this, ds has now become ds divided by cos theta. The magnitude of that angle has changed.
But direction of ds is that of normal.
Is that to the normal? So we'll have to deal with that at this stage. Okay? So now we can ask, what is the angle between the j and the n hat? That also involves cos theta. So this term here will involve a cos theta sitting outside and the old modulus of j times ds sitting outside. So now you can see, sorry, ds I've already written there. Now you can see that the cos thetas go away. So the answer is actually the same. And this is just to show you that just by cutting it, which should not change the answer, why you put in this factor of j dot n times ds. Because now all you're looking at is, given a surface, look at the current that is going in the direction of this vector, either in or out. It could equally well be pointing in which case particles are coming from the outside to the inside, or it could be pointing out. So I will give you some problems on this just to make sure that there is no confusion about how we define this. But this is just how it's done in, I mean, the rationale for what we've been doing in a more pictorial way. Okay? All right, so now we have defined this quantity, we have defined this conservation law, we have written it in the form of a continuity equation. And now let us try and see how to solve this equation in a particular way. And we had begun to discuss this the last time. We said that the simplest way of solving it is using a Fourier transform. So let's just go back to describing what that quantity is. So suppose I have some quantity f of x. The Fourier transform of this quantity is integral minus infinity to infinity dk e to the power I k x times the function f of k. Okay, so f of k, let me put a hat in there just to make sure that you don't confuse it. It's a different function, but these are related through a Fourier transform that looks like this. The inverse transform takes f of x and gives you back a f hat of k. And that's written as 1 over 2 pi integral minus infinity to infinity dx e to the power minus I k x times f of x. Okay. So now let us go back to this equation and try and see how we can apply it. So for simplicity, I will just use the equation in one dimension, which is delta rho of just ordinary x times t by delta t is d times delta squared by delta x squared of rho of x comma t. Okay. So everywhere I have rho of x and t. Let me substitute this. So I can, instead of f, I can just put rho here and rho hat here. So this is just delta by delta t of the integral minus infinity to infinity dk e to the power I k x f hat of k comma t, because this is where the time dependence actually appears. It's only the space dependence that I have Fourier transformed away. But this function is still a function of time. So I should put a rho here and not the f anymore. Okay? I have just said this is the definition of my Fourier transform. I can take any function that is Fourier transformable and write it in this manner. Instead of f, I now have a function rho. So I'm just applying this to both sides. I'm just Fourier transforming both sides of this equation. That means to say I'm multiplying by a factor of e to the I k x, and then I'm integrating over all values of k. So this quantity here is actually rho of x comma t, and this is delta by delta t of rho of x comma t. I've just written it using this Fourier transform. Okay. So now on this side, let us write d here, and now I have delta by delta x squared of rho of x and t. What does that look like? So now notice that delta by delta x of f of x, look at this equation here, is the same as delta by delta x of integral minus infinity to infinity dk e to the ikx f hat of k. Correct? I am just doing the same thing here. I am taking a derivative of this, therefore I must take a derivative of this. Okay? When I take a derivative of this, the only object this operates on is this quantity here, because this doesn't depend upon x, this doesn't depend upon x, and the limits don't depend upon x. So the answer is that delta by delta x of f of x is the Fourier transform of a function which is I k times f hat of k. Okay? Why is that? When I take the derivative inside here, it pulls down the factor of I k, but otherwise leaves everything else the same. So this is integral minus infinity to infinity dk I k e to the ikx f hat of k.
The integral remains unchanged.
Apart from the factor of ik, because this delta by delta x operates only on this. It only sees this because it's the only place it depends upon x. So when I take the derivative, it pulls down the factor of ik from here. It leaves e to the ikx because that's how derivatives act on exponentials. Then it leaves this here because it doesn't care about it. So then it looks like this. Similarly, delta squared by delta x squared of f of x is again operating this on this part. It doesn't care about the k, it doesn't care about the f hat of k, it doesn't care about dk. Again, it only cares about this. So this will be ik squared f hat of k. So take the Fourier transform of k, multiply by ik squared, and then this object Fourier transform the whole of it in order to get the quantity on the left hand side. Okay. So then what I will have here is d into integral minus infinity to infinity dk, so ik squared e to the ikx rho hat of k comma t. I put the rho hats on both sides because I am now taking the Fourier transform. Okay. Let me now simplify this, and now I will write this as delta by delta t of, yes, write this, minus infinity to infinity dk e to the ikx. So now I can put rho hat of k comma t here. I have pulled this particular factor out. I only have this acting upon this here. And the right hand side is d times integral minus infinity to infinity dk e to the ikx times the factor of minus k squared times rho hat of k comma t. Okay. Now note that this part is common to both sides. Okay? So essentially what this means is that simplifies into an equation for rho hat of k and t. That if I solve this equation, then I know what rho hat is. And in order to solve this equation, I have to know what rho hat is at time t equal to 0, because this is the first order equation in time. Okay? This is really all that is different between this and this is that I take the Fourier transform on both sides. Therefore, this quantity inside on both sides must be related to the quantity on the left, must be related to the quantity on the right. Okay? Now this equation, I know how to write down the solution for. Okay? And I will show you how to do it. All that I need is rho hat of k comma t is rho hat of k comma 0 e to the power minus d k squared times t. Okay? So I wrote down the solution, but you should convince yourself that this is actually fairly sensible. There's nothing unusual about it. Okay? All I'm saying is that dyt by dt equal to a times y or minus a times y of t. This is essentially the equation that I'm solving here. So some variable y that depends upon t, which takes the place of rho hat of kt. There's no complicated here. And for each, the a here is minus dk squared, and this has the same sort of solution that I have here. F hat is, this is just a definition. So I have not told you what f is. This is just given any function f. This is how I take the Fourier transform. Rho hat is what f hat k, the role plays the role of what f hat k. It's a Fourier transform of rho of x. Remember that given any rho of x, I can go in Fourier space to rho of k. And given any rho of k, I can go back to an inverse Fourier transform to rho of x, with some conditions on how well behave their functions, which means basically they should not behave sort of badly as you go very far to infinity. And that's a sort of mathematical condition which we won't worry about too much when we discuss this now. Okay? So having done this, we have essentially this equation here, which we recognize as being a very simple, almost the simplest type of differential equation that you can have. Let us check this and see that it works. So here is the solution that we have proposed for this. First of all, at t equal to 0, rho hat of kt is rho hat of k0 at t equal to 0. That's just sort of almost a definition of what it should be at t equal to 0. But otherwise, at any general t, if I take one time derivative, so I write delta rho hat by delta t of rho hat kt, I must take another, the same time derivative here. That pulls down the factor of minus dk squared t, minus dk squared, leaving the c power minus dk squared t. But that's exactly what I had here. Okay? So this is a solution which we can now test, showing that this is by actually doing this derivative here, we can check that this is actually the solution of that differential equation.
So how did we come from here to here?
We said that now this is the same as doing the Fourier transform of whatever quantities was inside here. So I had rho hat here, I had something operating on rho hat, something operating on rho hat here by multiplication. So it's just this part remains the same on both left and right. Therefore, this condition between this derivative of this and minus k squared times this must always be satisfied. Okay, that's essentially what I've done here. Pull that out. It's the same as just Fourier transforming this, no? Suppose I had an equation like this. I can Fourier transform both left and right. And that's exactly what I have done here. Nothing else. So now we need to try and understand what this particular equation is. So now we need to solve this. So let us assume that rho of x at time t equal to 0 is just delta of x, which means it is a function that is non-zero only at x equal to 0 and 0 everywhere else. It sort of goes off to infinity here. So this is delta of x as a function of x, and we introduced it the last time. Okay. So then what is rho hat of k comma t equal to 0? That is just the Fourier transform of the delta function. So that number will turn out to be a constant, which is why we can start with that particular assumption there. So this is just the inverse Fourier transform that I had there, which is 1 over 2 pi times the integral minus infinity to infinity e to the power minus ikx delta of x. Okay? I've just substituted this quantity here in this particular definition that sits here. So what I have here is that this quantity is 1 over 2 pi. This is what it is. So I now know this part of the equation. Now we need to try and solve the second part of this. And Fourier transform rho hat of k comma t. So rho of x at some time t is this first part, rho hat of k comma 0, which is 1 over 2 pi times the inverse Fourier transform of the subject, e to the power minus d k square t, which is the further factor of 1 over 2 pi, and integral from minus infinity to infinity e to the power minus ikx over e to the power plus ikx here times e to the power minus d k squared times t and nothing else. Is that okay? Now we are going back. I have now told you what is rho hat of k comma t. Okay? But you still don't know. What you want to know is what is rho of x comma t. The whole logic behind the Fourier transform is that you can switch cleanly between f of x and f of k. What we did in this case was to find an equation solve that f of k followed. That equation was this equation, where instead of f I have the rho hat. This I could solve very easily. But now remember, this is still in k space, still in Fourier space. We must now go back from Fourier space into real space. Because then we would have had to solve this differential equation. So there are several ways in which you can solve this. This is one particularly simple way that tells you, that illustrates something apart from teaching you a little bit about the Fourier transform, which we will see later as well. Okay? Alright, so how do we solve this integral? So here is an integral that is e to the power ikx, e to the power minus dk squared t times dk. Now we need to figure out how to solve this particular integral. Okay? So let's just give you one example, which is an integral minus infinity to infinity d, it doesn't matter what this is, so let me just say d, let's see, call it dx, e to the power minus a x squared plus bx. This is e to the power b squared over 4a, and the normalization here should be root of pi divided by pi times a, I think. Root of pi divided by a, sorry. This is one of these useful integrals that is nice to remember. You can always, there are many ways in which you can write these integrals. And another integral, if you remember, that I wrote down the last time was integral minus infinity to infinity dx e to the power minus a what x squared over twice sigma squared was square root of 2 pi times sigma. That's the same as this integral, except that instead of a I have 1 over 2 sigma squared and b is 0. So these are integrals that is convenient and useful to remember, because from these you can go back and derive what the right answer is. How did I get this quantity? Yep. So if I have some function of k, f hat of k, I can get to f of x by doing this particular operation. So now I have to ask, what is my f hat of k? Well, my f hat of k now is a function here, which also depends upon time, but it depends upon time in a simple way. I'm only interested in the k dependence. So I now take this and I Fourier transform it back. I put this factor here, which is the same as this factor. I integrate over k, which is what I'm doing here. And the factors of 1 over 2 pi come one from the initial condition. And I think I should not have a further 1 over 2 pi there. I think I don't have further 1 over 2 pi. I just have single 1 over 2 pi. Okay.
So there are one.
No, this is fine.
No, the initial state is 1 by 2 pi.
That's correct. So that is where the 1 over 2 pi is.
And the inverse Fourier transform has one another.
I thought it's this relationship that I'm using. It's a direct Fourier transform because I have f hat of k, which is this quantity here. So it's this top line that I'm using. Okay. So here I had to use the inverse Fourier transform because I was specifying the initial condition in real space. So to get rho hat of k at t equal to 0, I had to do this, which is why I got the 1 over 2 pi. But I don't need to do it here.
So we're not going back, we're just substituting into that.
We're just substituting into that right now. Okay. So now let us, given this particular relation, let us try and identify between here and here what are the points that are similar. So I want to now stare at this particular part here. I want to stare at this particular part here. I recognize the integral between minus infinity and infinity is the same. Whether I call it dk or dx doesn't matter here at all. It's just a dummy variable. So I should be able to read off from here in this answer what is the answer to that. So the way I would do that is, first of all, what is A? A is the same as minus d dt, right? Minus dt. In fact, it's not minus, it is plus, because the sign here is minus and the sign here is minus. So it's d times t. All right. Now what is b? B again, look here, it is ik. I times x. Okay. So then what should the answer be on the right hand side? This integral then, this is square root of pi divided by a, which is d times t. Okay. E to the power b squared, which is minus x squared divided by 4 times a, which is 4 times d times t. Is that okay? Just wondering if I got all my factors correct. And
So there's a 1 by 2 pi.
there's a 1 by 2 pi. So that is correct. So now what I have here is rho of x comma t equal to 1 over 2 pi into square root of pi divided by d times t into exponential of minus x squared divided by 4 times d times t.
Do we have an advantage taking rho as a delta function?
Let me just finish this and then we will see exactly where that comes through. So it is now get rid of various factors. So the pi and the square, this can be written as square root of pi squared, that gives me a factor of pi. I can take this inside the square root, that gives me a factor of 4. So this is 1 over 4 pi dt to the power 1/2 exponential of minus x squared divided by 4 times d times t. And that is the solution of the diffusion equation, starting from a condition which is a delta function at t equal to 0. Okay?
Initial condition is the inverse function.
So the initial condition came in this factor of 1 over 2 pi here. The fact that it was constant. And then we simplified it to this particular form. Okay. So now let us plot this function and see what it gives. So here I'm plotting rho as a function of x at different times. And here I will plot x. At time t equal to 0, the smaller the t is over here, you can find that basically this is 1 over a very small number is a very large number. An exponential of minus of a very large number is practically 0. It's only non-zero when this is also small, because then I have a large number multiplying a very small number. So it's reasonable that in some limit like that, as t becomes very small, this quantity basically behaves very sharply. Sort of does this. And in the true limit that t goes to 0, this is the delta function. If you look at it for any other larger time, this is perfectly well behaved. For small x, for x equal to 0, this number is always goes down as a factor of 1 over t to the 1/2. So let us look at that. That means that as time goes on, the value here keeps coming down. The amount it comes down is by a factor of 1 over t to the 1/2. Is that clear, Kiranmai?
Yeah, I'm thinking, this is, again, we have just got rho x of t, we are saying it's delta function, but when we took rho cap, that was the Fourier transform of the delta function.
Yes.
So if we plot that thing, the Fourier transform, it will be a flat line.
Yes,
And
exactly.
why have done all this? We're just going back and forth and we have got the delta function back.
We've got the delta function back because that is a test for us to see that our initial condition has been incorporated correctly.
And what was the initial condition?
The initial condition was that it's a delta function here. So when I do the final solution of rho of x and t, when I set t equal to 0, I should have a delta function. Now this is a delta function. This satisfies all the properties of a delta function. I was just pointing out to you physically why that was so. I said it has to come down, the smaller the t is, the smaller the x must be, because for if I keep x finite and t goes to 0, then because this 1 over t is so small, this quantity comes down very, very, very fast. It's practically 0. So it only can be non-zero, something like non-zero, when x is very close to 0 itself. Because then I'm multiplying a very small number, which is x, by a very large number, which is 1 over t for small t. In the limit that t goes to 0 is equal to 0, then precisely at x equal to 0, when this function can contribute, nowhere else. Okay? Now also notice that let me set x equal to 0 and look at it at different times. If x equal to 0 for any finite time, this always is 0. Therefore, the only dependence on the time can come from here. And this is 1 over t to the half, which is a number which becomes smaller and smaller as t becomes larger and larger. So at x equal to 0, as I go out change time, this number comes down. And from here, because the fact that this is a Gaussian, we can reconstruct other properties. For example, over here for this time it might look like this, for this time it might look like this, for this time it might look like this. For now it's a full row of x. x0 is only telling me about this value here, this value here, this value here. So this might be row of 0 at time t equal to t1. This is row of 0 at time t equal to t2, which is greater than t1. And similarly, this is row of 0 time t equal to t3, which is greater than t2 and t1. So this just says that the 0 value, the value at 0 is going down in time. The remaining part of the graph I can just plot because I know what this function looks like. It's a Gaussian, which means it's symmetric about between left and right. It has to come down because the exponential of minus x squared. And from here I also know what the width of the function is. The width is increasing with time as this particular object. And why do I know that? Because I know that if I take a normalized Gaussian, minus infinity to infinity, dx e to the power minus x squared over 2 sigma squared, this quantity, if I look at what is the value of x squared here, this quantity is basically sigma squared. And I should of course properly normalize it here by putting 1 over square root of 2 pi times sigma. Okay? So just reasoning from this here, the average value of x squared is sigma squared. So that tells me how broad it's becoming as a function of time. Okay? So just looking at it directly from here, x squared average, which is like the width of this distribution, this is equal to twice the dimension, twice dt, because now d appears explicitly here. I'm just comparing this with this. Okay, clear? All right. So now, what have I done so far? I have just stayed so far in one dimension. But now I can easily do the more complicated version, which is delta of rho of vector x comma t divided by t. Delta t is d times del square of rho of vector x comma t. Okay? But this is also very easy to solve. And the reason is that this just breaks up into densities along x, y, and z. These are sort of separate equations. So the product is just a product of that solution. And this just becomes here a slightly more complicated version. So rho of x comma t, now it's a vector, not just a scalar, is 1 over 4 pi dt to the power 3 divided by 2. That comes from the dimension, into e to the power minus x vector square divided by 4 dt. So this is a generalization to 3 dimensions. And in general, if it was in 2 dimensions, this would be 2 by 2. In 4 dimensions, it would be 4 by 2, etc. That's the only place where the dimension comes in. Otherwise, this part looks very much the same as the other part. And now we can also use this particular result here to say that the width of the distribution, which is x squared plus y squared plus z squared average, which is the width, technically the width squared, is 2 dt plus 2 dt plus 2 dt, because each of these I can separately average. This is just 6 times d times t in 3 dimensions, and is twice the dimension, diffusion constant, times t in general dimension. We had the one-dimensional result here, we had the 3-dimensional result here, and therefore the more general result for what is the width of the distribution. The width square is a function of the distribution as a function of time. Okay? Is that clear, what we've been doing so far?
If the initial state is other than x, how will be the plot? If other than x equal to 0.
So where that initial state comes in is this particular factor here. So that initial function state, if suppose you shifted it at some point, then this function would be, instead of x squared, would be x minus x naught squared by 2 sigma squared. If it was a delta function centered at some other point x naught rather than the origin, this would be, it would spread about that point. So finally, for a diffusing particle, remember what we've been trying to say. Suppose I started the diffusing particle at the origin here, and it sort of moved around. As time goes on, the probability of finding it at different paths actually changes. For each of this, if I looked at the distance between the final position and the initial position as a function of time, which is what we called delta, which is r at time t minus r at time 0. The location of the random walker at time t minus the location started out with. This was my quantity called delta. Now, if I have delta squared and then I average it.
This x square is sigma square, right?
One sec. No, x squared is not sigma squared.
X square is sigma square, right?
X squared averaged, which is taking this probability, multiplying it by x squared, that is sigma squared. Sorry, there shouldn't be a bracket there. There shouldn't be a bracket there, my fault.
The radians, I mean, why is the radians the width?
It's a width squared. It's a width squared. It sort of tells you how broad this particular function is. So in this case, sigma would be normally referred to as a width. Sigma squared is the variance, as you point out. So I've just been a little careless about nomenclature here. But I wanted to do that because I wanted to define why this result is important in the context of notation that we used earlier, which is delta squared. Delta is the distance between the position at some later time t minus the initial position. Okay. Now, this random walker can start in one realization, can start here and go here. If I do it again, it might go here. If I do it again, it might go here. And we've seen that. We have no control over it. It's some probabilistic function. So what we wanted to ask is, what is the probability that having started here, I land up at some distance far away from it? That is the same as the thing that I have calculated, the rho of xt, because that is the density of finding the particle at some distance r. So first of all, it's symmetric about r. It doesn't care where. It could be anywhere within a sphere contained in that region. It doesn't discriminate between right and left, forward, backward, up or down. But also, the region in which it's most likely to find it increases slowly with time, as 6 times d times t. And that is the result that we have. This is the width of the distribution, or the width square of the distribution behaves like this. Okay?
But there is no term, there's no R over there, right?
There is no r here, but first I went from being a scalar x to a vector x. So this is the probability, this is the density of particles at point x, given that they all started off at point 0. Equivalently, I can think of one particle that started off here and sort of wandered around and reached somewhere else at time t, and I could call this r of t minus r of 0. That is this particular vector here. Okay. The probability of it reaching here, having started off here, is really the same rho of x and t. Because rho is also, rho, we used many different terminologies or descriptions for rho. We said rho was the density of particles, but we started off by saying it's the probability of finding a particle at some different point if you started off here. It's that interpretation that I want to go back to. So the question is, what is the probability of finding the diffusing particle at position r at time t if I know that it started off at position 0 at time t equal to 0? That is a full function probability of r comma t. This is the probability distribution function, which is really the same as rho of r comma t, which is the same as rho of x comma t, the way I have defined it here. Okay? So suppose I started off at the origin and it goes up till here at some time t1, and by time t2 it has landed somewhere up here, etc. This quantity delta squared is some indication of what is the size of the sphere I must draw in such a way as to be reasonably sure of finding that particle. Okay. That is the width of the distribution, which is some measure of how far does it go. It's unlikely to go all the way here because there's very little probability here. It's most likely to be found here, but still there is some deviation from that. So, for example, I might say that, look, at small times I'm most likely to find it here. At longer times I'm most likely to find it anywhere here. At even longer times I'm most likely to find it anywhere here. What do I mean by most likely to find? Well, one way of thinking about it is, this is like a distance squared. So I can think of it as some radius of a sphere. It can be anywhere within that sphere. If I draw a sphere of radius so much, then I can assign a meaning to the fact that it's most likely to find it in this particular region.
So we make the radius equal to the width.
Yeah.
Defined by
If I say radius squared is equal to this delta squared, that radius squared increases in time. I can think of it as drawing a sphere of radius r, making the sphere slowly increase in size with time t, with the interpretation that it's have a high probability of finding the particle within that. It's not as though there is zero probability of finding it, it's just that it's very small. So most of the particles can be found within this region. Conversely, it's most probable that I will find my single random walker somewhere within this region. Okay. So it's instructive to sort of compare this quantity, let's say time t equal to, let's just say 1 second here. So then this would be 6 into d into 1 second. This would be the radius squared. Okay. Now let us look at t equal to 10 seconds. So radius after 10 seconds squared is 10 is 6 times d into 10. And after t equal to 100 seconds, the radius squared would be 6d into 100. Okay? But the radius itself is proportional to the square root of 1, the square root of 10, and the square root of 100, because I must take the square root. The 6d, of course, is the same factor throughout these things. Okay? So, even though the time has changed between 1 second to 100 by a factor of 100, the radius of the sphere that I must draw to enclose the particle has only changed by a factor of 10, which is square root of 100. Okay? So diffusion is not an efficient way of moving things across large distances, because as time goes on, it's not as though the region that you explore becomes sort of significantly larger as time goes on. And the reason for that is that a diffusing particle, even though it's sort of on average this thing is spreading out, it also comes back to regions where it's already been and hangs around here for a while. So that's why the sphere does not increase linearly with time.
But with this explanation of graphs, as the time increases, we can say that it becomes uniformly distributed, right?
At infinite time, it would be uniformly distributed. It would be a function that will sort of look anywhere like this.
So that does mean that the sphere is also...
Yeah, so in order to discuss what happens at infinite times, you should say what are the boundary conditions that you impose on the particle. Suppose there's some box like this. Then the probability can only grow until it becomes uniform within this box. Alright, it's only when the box is taken to infinite that I can assign what does it mean for it to actually keep on going and changing like this. So this is one thing to carry home, that the diffusion constant, particles that move by diffusion are not very efficient at exploring large regions of space and time, because the amount of space that they explore only goes as the square root of the amount of time, not as the amount of time itself. Contrast this with something that is moving with fixed velocity. Suppose I have something moving with a velocity 1 centimeter per second. Then in 1 second it has moved 1 centimeter, in 10 seconds it has moved 10 centimeters, in 100 seconds it has moved 100 centimeters. Okay? On the other hand, your diffusing particle has moved, say, so much 1 centimeter in 1 second, but only much less, square root of 10 on average in 10 seconds, and only about a distance of about 10, a sphere within a sphere of about 10 in 100 seconds. Okay, so let's just do one quick estimate. So first of all, we said that most molecules in a cell, all molecules in a cell, are subject to thermal fluctuations. Because of those thermal fluctuations, they can move around. If it's not attached to anything, it diffuses around. For example, it may move around in the cytoplasm. So let us take something like the lysozyme, which is a small antibacterial protein. And I will tell you that the lysozyme has the diffusion constant, which is about 10 to the minus 5 centimeters squared per second. What I want you to do is to estimate the time it takes to cross a 1 micrometer distance, or approximately estimate, given what you know now, how you would do that. So here what you would do is, you would say r squared is proportional to or equal to 6 dt. This is the distance it goes on average. So one way you can estimate this is to replace r squared by 1 micrometer squared. 1 micrometer squared divided by 6 times the diffusion constant, which in this case is 10 to the power minus 5 centimeter squared per second, is some estimate of the time that it takes. Now you have to be a little careful about changing units here, because this is in microns, this is in centimeter squared. So let us try and estimate that. We can convert everything into centimeters, that makes it a little easier. So 1 micron squared is 1 into 10 to the power minus 6 meters. 1 meter is 10 to the 2 centimeters. So here I have centimeters squared. Is that correct? Over here I have the number 6 into 10 to the minus 5 centimeter squared per second. So the centimeter squared and centimeter squared will go here. This will be a unit of seconds. So let us estimate this. 10 to the power minus 6 plus 2 is 10 to the power minus 4. 10 to the power minus 4 squared is 10 to the power minus 8. Correct? Divided by 6 into 10 to the power minus 5, which is 1/6 into 10 to the power minus 8 plus 5 seconds. 1/6 is 0.166 into 10 to the power minus 3 seconds, which is approximately 1.6 into 10 to the power minus 4 seconds. Is that correct? Is that what you get? So here is how you can use knowledge of diffusion constants to estimate how far they actually move. So now estimate for me, suppose you have a test tube here and you have a lysozyme molecule moving here and moving around. How long will it take to move by 1 centimeter? How long will it take so that the probability of finding it has spread out from the probability where you put it initially to a region of about 1 centimeter? How would you do that calculation given what we've done now?
So diffusion constant is same as this.
Diffusion constant is the same. It's just that instead of asking how long will it take to move 1 micron, which is typically the size of some bacterium here, I want to ask how much time will it take to diffuse around a distance of about 1 centimeter, which is a much larger distance. So it's clear how that has to be done. Instead of 1 micron squared, I must have 1 centimeter. But then that helps because I don't have to worry about conversions between centimeters and meters. I have 1 centimeter squared divided by 10 to the power minus 5, put a factor of 6 in here, 6 into 10 to the power minus 5 centimeter squared per second. Remove this, this becomes 1/6 into 10 to the power 5 seconds. How much is 10 to the power 5 seconds? So we discussed this at some point in when we were estimating time scales. How many seconds are there in a day?
100 years is 10⁹ seconds.
So 86,400 seconds in a day, which is very close to 10 to the power 5 seconds. So this takes approximately 1 day to diffuse around by 1 centimeter. Okay.
So this is an average number, right? 1 day.
It's always an average.
It may reach before it and then go back.
It could. So this is always an average. Whenever we talk about it, we are putting an average time to move 1 day as approximated in this particular way. But it's possible that if you run it 10 million times, maybe 1 time or 2 times, it will probably go away, maybe within a matter of minutes or hours it will do that. But overwhelmingly, if you make a measurement, they will all be typically of like 1 day.
So as the distance increases and the result, is it like good? Because diffusion is like the more smaller, shorter is the region, the more exact results you will be getting. So because the region is larger, the distance, so will there be a lot of error?
No, there won't be, because the only requirement of diffusion is that it should be, the motion of this should be essentially randomized. So the larger you, if you had a very, very short times, then maybe this particle will not encounter any particle as it moves. That's not a situation where diffusion operates, because it's moving without touching anything. It's essentially moving what the technical word is ballistically. It's only once when you go to larger times that this can move here, then get scattered off something, then come here, then do this. And then sort of at long times the trajectory looks very long and complicated and twisted up. So actually this should work somewhat better at long times rather than at short times. The only difference is when you consider things that are confined, like this, suppose this is a test tube. Once this object has diffused to a distance which is comparable to the size of the walls of the test tube, it can't go any further. Okay. So suppose I plotted the magnitude of r squared, so mod of r squared, as a function of time. This will go linearly in time because r squared is proportional to t until such time as r squared becomes of order d squared. And then this will saturate because now it cannot go any further. It's the maximum distance that it can go. So whenever you see sort of experimental situations where r squared goes up and then plateaus, this is a suggestion that it's being constrained or confined in some manner. Okay. The other thing to watch out for technically is that it's not just often a simple particle with a bunch of tiny little particles that you can't see that lead to Brownian motion. It could be embedded in a much more complicated matrix of things. You can have actin filaments, you can have motors moving on those filaments. So what are the effects of those motors and all of these things happening on the motion of the colloidal particle at long times? That could potentially be a more complicated question. But by and large, the simple estimate will always work. So now there are several, having now motivated the diffusion constant, giving you a magnitude of the diffusion constant, showing you how it works and doing these estimates, maybe the next time let's ask the fundamental question of how do I calculate a diffusion constant? What does it depend upon? Does it depend upon the size of the object that is moving? Does it depend upon the mass of the object that is moving? Does it depend upon any property of the surroundings in which it is moving, for example, the temperature or the viscosity or anything like that? That's what we want to now try and understand. So in the next class, what we will do is try and answer this question. What is it that the diffusion constant is related to? How do we determine it? And how do we estimate what is the diffusion constant?